Hello everyone, this will be the second part of lattice vibration. So let's try to recap whatever we have done in the previous video. So in the previous video we have solved the dispersion relation for a linear chain of atoms. So where we have assumed it the linear 1D atoms as a spring mass system where each atom is considered of mass m and it is connected with its neighboring atom with a spring constant beta, and in the state of displacement this each atom is slightly disturbed from its mean position with an amplitude of un, so that its neighboring atom will also get displaced with amplitude un plus 1, and in the previous one we get un minus 1. So these were the displacement from the mean positions, and we have assumed the solution for this displacements as a periodic solutions which have this form of a plane wave omega t minus k and a. So where k represent the wave vector of this plane wave and omega is the frequency of that plane wave. So now the similar solutions can be given for un plus 1 and un minus 1, and we have seen that un plus 1 was nothing but e raised to power minus iota ka un, and un minus 1 was e raised to power iota ka un. So from the Hooke's law we have also calculated the force acting on the nth atom. So that was Fn equal to beta un plus 1 minus un. So this is the force because of this spring, and then plus beta un minus 1 minus un. So this is because of this second spring. So if we simplify this, then we will get m d square un by dt square equal to beta un plus 1 plus un minus 1 and then 2 un. And we have substituted all these solutions here in this equation of motion, and we got the dispersion relation as omega equal to 2 divided by a vs the mod of sine ka by 2, where this vs was under root c by rho, and it is very specific to a lattice. So let's try to plot this dispersion relation. Now notice here that this frequency of the vibration, it has to be a positive quantity. So this means that the plot should be only in the first and second quadrant. So the plot will be in the first and second quadrant, and it will be a series of positive sine lobes. Where this frequency will again vanish at 2 pi by a. So this is the value corresponding to sine ka divided by 2 is equal to 0. This means that ka by 2 is equal to pi. This meaning that ka value is 2 pi by a, or in the multiples of 2 pi by a. So 4 pi by a and so on, 6 pi by a. And similarly on the negative side, 2 pi by a and minus 4 pi by a. Now here the interesting region is corresponding to this particular region. So this is pi by a and minus pi by a. So this particular region is very interesting, and we will be doing our study in this particular region. So let's try to zoom this particular region. So this particular region from minus a to minus pi by a to plus pi by a is known as first Brillouin zone. And we will see the limiting case of our dispersion relation in this first Brillouin zone. So the first limiting case will be corresponding to k tending to 0, or what I can say in low frequency range, or long wavelength limit. So in that case, our sine Ka by 2, the argument of sine will be very small, so we can approximate it by Ka by 2. So in that case, our dispersion relation will become 2Vs divided by A and then Ka by 2. So this means that our omega will be A, will be K times Vs. So this is the dispersion relation in long wavelength limits. Now we define phase velocity. V phase as omega divided by k, and this represents the rate of advance of a point of constant phase along the direction of propagation, wave propagation. So we know that our plane wave has a exponential raised to power iota omega t minus kx type form, and this phase velocity is representing the rate at which the point of constant phase it is moving in the direction of wave propagation. So let's try to find phase velocity in this case. So it is very easy then, that you can see from here that V phase velocity will be equal to the sound velocity in this particular limiting case. Now we also define our group velocity. Group velocity is defined as the velocity with which the wave transmits the energy along the direction of propagation. So this is given by d omega by dk, and in this particular case also this will be equal to Vs. So in long wavelength limits, the phase velocity is equal to the sound velocity, and it is equal to the group velocity. So this is an important result to remember, because this is the similar situation which happens in a continuous line. So for a continuous line, or I can say a non-dispersive medium, so for a wave transmission through a non-dispersive medium, you get a similar kind of situation where phase velocity and group velocity are equal. So you can conclude that in the long wavelength limits, that is lambda is very larger than the lattice spacing. So in this limit, this discrete system of atoms, so basically we considered the atoms to be discrete, and this system is behaving as a continuous line. Now let's see what is the behavior of the vibrations in this case. So here you can see the behavior of lattice vibration when the wave vector k is very low. So in that case, this forms a continuous wave, right? And this is a wave which can transmit energy from one point of the lattice. So basically the 0th atom to the 20th atom, it can transmit energy. So in this long wavelength limit, so here you can also see that the wavelength of this continuous wave, it is very large than compared to the lattice spacing between any two atoms. So you can see this clearly here. In this situation also, here the wavelength is tending to infinity, and as compared to the lattice spacing. Now let's see the behavior of dispersion relation when when this k vector is in the middle range. So in that case, at higher frequencies, omega will be equal to 2 Vs divided by A and then sine Ka by 2. So this implies that omega by K, which is nothing but the phase velocity, will be equal to 2 Vs divided by A K sine Ka by 2. So here you can see that this phase velocity is a function of wave vector k. So this represents dispersion, where the related quantity is dependent on the frequency or wave vector of the wave. Similarly, you can calculate group velocity, which is given by d omega by dk, and you can differentiate our dispersion relation, and then you will get 2 times Vs by A and then cos Ka by 2, and then differentiation with respect to k will give you A by 2. So A by 2 will cancel out this, so you will get Vs cos Ka by 2. So here also this V group velocity is also a function of wave vector k or frequency, right? So this particular region is known as a dispersive region. Now let's see the behavior at the zone boundary. So at k equal to pi by a. So at k equal to pi by a, the frequency will be maximum. So that will be under root 4 beta by m. You can see here in the graph also at this pi by a, the frequency is maximum. So this value is under root 4 beta by m. And in that case, we can calculate group velocity as d omega by dk, and since it is independent of k, this means that the group velocity will be 0 and the phase velocity, which is omega by k, will be equal to 1 by k under root 4 beta by m. And this is equal to, if you put the value of k, then you will get a by pi times under root 4 beta by m, and in terms of velocity, then you will get a by pi then 2 Vs by a. So a to a cancels, so this will become 2 Vs by pi. So this is the phase velocity at the zone boundary. Now since the group velocity is 0, so this means there is no transfer of energy. There is no transfer of energy, so this represents a standing wave. So let's see the lattice vibrations at the zone boundary. So here you can see the lattice vibrations forms a standing wave, so this do not propagate any energy through the lattice. Now if you notice that at zone boundary at k equal to pi by a, your lambda will be equal to 2a, right? And if you notice from the Bragg's reflection condition, that is 2d sine theta is equal to n lambda, and for normal incidence and n equal to 2, then also you will get lambda is equal to 2d. So this is a very similar condition for Bragg's reflection also. So this means that this above condition is equivalent to the condition for the Bragg's reflection. Also note that there is a limit, upper limit to the value of frequency. So there is a upper cut off value, so that is 4 beta by m. So this is the maximum value of frequency which can propagate through this lattice. So you cannot get a higher frequency than this 4 beta by m. So this means that this lattice behaves as a low pass filter which transmits only if the frequencies are between 0 to this maximum value. So for example, this upper cutoff frequency is given by 2 Vs by A, and let's take an example of A is equal to 10 raised to power minus 10 meters, and the value of Vs, the sound velocity, around 10 raised to power 4 meter per second. So in that situation, The maximum frequency which can be transmitted will be omega max is nearly equal to 10 raised to power 14 Hz. So this is the maximum frequency which can be transmitted through this lattice, but this particular lattice. So you can figure it out that this particular frequency is the upper limit, and below this any electromagnetic radiations can also induce the forced vibrations. So this is it for this particular topic. We will meet next time with the vibration of 1D diatomic lattice. So thank you for watching this video.